Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will see some consequences of Lagrange's theorem. Let us consider first corollary. The index of any subgroup of a finite group is a divisor of the order of the group. In the proof, we assume that G is a finite group of order n and let H be a subgroup of G of order m. We know the Lagrange's theorem, and by this theorem the number of distinct right or left cosets of H in G is denoted by index of H in G equal to, we know that it is equal to order of G divided by order of H. This implies order of G equal to index of H in G into order of H, and this implies index of H in G divides order of G. This proves that the index of any subgroup H of a finite group G is a divisor of the order of the group G. Now consider second corollary. If G is a finite group and A belongs to G, then order of A divides order of G. In the proof, we assume that G is a finite group and A belongs to G. We know that order of an element of a finite group is finite. Let order of A equal to m. We have assumed this order of A equal to m. Now consider the cyclic group generated by A. Cyclic group is denoted in this manner. Cyclic group A equal to set of all A raised to n such that n belongs to Z. Then order of the cyclic group equal to m, as we have assumed this order of A equal to m. Order of this cyclic group is m, as order of A equal to m. Hence cyclic group of A equal to set of elements A raised to 0 equal to E, comma A raised to 1, comma A raised to 2, comma A raised to 3, comma dash 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 A raised to m minus 1, and this set is complete. That means cyclic group of A contains m elements. These are m minus 1 and this is identity element is 1. So that total m elements since order of A equal to m. Thus, if G is a finite group, then order of A, we have considered the cyclic group which contains elements m. Therefore, by Lagrange's theorem, we know that Lagrange's theorem, that is order of A divides order of G. Hence, order of A divides order of G, that is m divides n. Since order of A is m, order of G is n. Now consider corollary number 3. Statement is, if G is a finite group of order n, then for all A belongs to G, A raised to n equal to E, where E is the identity element of group G. In the proof, we assume that G is a finite group and A belongs to G. Suppose that order of G equal to n and order of A equal to m. Then by above corollary, order of A divides order of G, that is, this implies m divides n. Hence, n equal to mk. That is, we know that if 10 divides 5, then we know that 5 equal to 2 into, if order of A divides order of G, that means m divides n, that is, this implies n equal to mk. Hence, if 5 divides 10, then this implies 10 equal to 5 into 2. So that if m divides n, this implies n equal to mk for some positive integer k. This implies a raised to n equal to a raised to mk, since n is equal to mk, and this can be written as a raised to n equal to a raised to mk. This can be written as a raised to m raised to k, but a raised to m, we know that a raised to m equal to e. A raised to n equal to e. So that this is equal to e. A raised to m equal to e raised to k equal to e. So that this implies a raised to order of g equal to e. A raised to n means order of g, so that a raised to order of g equal to e. That means if G is a finite group of order n, then for all A belongs to G, A raised to n equal to E, where E is the identity element of group G. This implies A raised to order of G equal to E. Now we consider one definition of Euler's phi function. Phi of n is defined as follows. For any integer n, we define phi of 1 equal to 1, and for any n greater than 1, phi of n is defined as the number of positive integers less than n and that are relatively prime to n. This, if any integer n is greater than 1, phi of n is defined as the number of positive integers less than n and that are relatively prime to n. Now we consider some remarks. Relatively prime. Here two numbers are relatively prime, that means their greatest common divisor is 1. That is 3 and 5 are relatively prime since their greatest common divisor is 1. 3 equal to 3 into 1. 5 equal to 5 into 1. Their common factor is 1. These are relatively prime. 3 and 5 are relatively prime. Now we consider some remarks. Number 1 remark is phi of 6 equal to 2. We have defined phi function as for any integer n, we define phi of 1 equal to 1, and for any n greater than 1, phi of n is defined as the number of positive integers less than n and relatively prime to n. So that phi of 6, that means number of positive integer must be less than 6 and they must be relatively prime. Phi of 6 equal to 2, which are the numbers 1 and 5. Since 1 and 5, they are less than 6 and they are relatively prime since their common factor is 1. These two are relatively prime. Also phi of 10 equal to 4. since the numbers 1, 3, 7, 9 which are less than 10, these are integers. Numbers means they are integers. 1 and 5 here less than 6 and they are relatively prime. That means their common factor is 1. Here also 5 of 10 equal to 4. Here 1, 3, 7, 9. These are integers, positive integers, and they are less than 10 and their common factor is 1. Take any two integers, their common factor is 1. And these four numbers are less than 10. So that 5 of 10 equal to 4. Second remark is if P1, P2 up to Pn are distinct prime factors for n greater than 1, then phi of n equal to n into bracket 1 minus 1 upon P1 bracket complete into in second bracket 1 minus 1 upon P2 bracket complete into dash 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 last bracket is 1 minus 1 upon Pn bracket complete for n greater than 1 where P1, P2, Pn are distinct prime factors. Then phi of n equal to this term. Third remark is if m comma n are co-prime means they are relatively prime. Relatively prime means their common factor is 1. And phi of mn equal to phi of m into phi of n where m, n are greater than or equal to 1. That is m and n are co-prime or relatively prime, then phi of mn equal to phi of m into phi of n. Now consider one definition. Two integers a and b are said to be relatively prime if their greatest common divisor is 1. We have seen in this case. Second definition is, that means for example 5, 7, their greatest common divisor is 1. That means their common factor is 1. Second definition is let a comma b belongs to z and n belongs to n. Then a is said to be congruent to b modulo n if n divides a minus b. It is denoted as a is congruent to b modulo n. For example, 12 is congruent to 2 modulo 5. It means 5 divides 12 minus 2. Also, you can take another number, that is 10 is congruent to 1 modulo 3 since 3 divides 10 minus 1, that is 3 divides 9. Now consider the statement of this theorem. This is only for statement, not proof for your syllabus. Statement is if a comma b belongs to z and b is greater than 0, then there exist unique integers q and r such that a equal to bq plus r, where 0 is less than or equal to r less than b. You can take examples of this statement also. That means 11 divides 2. Then we get remainder as 1. We can write 11 as 2 into 5 plus 1. That is a equal to pq plus r. R means 1 and this r must be less than this b. R must be less than this 2. You know this.